Welcome to the deep dive. If 2023 was the year AI models got huge, and 2024 was when they really learned to talk,
Mm,
then 2025 was the year we all had this kind of aha moment.
right.
We realized that intelligence isn't some single monolithic test score. It's a spectrum. It's defined by a fundamental duality: biological intelligence, BI, versus artificial intelligence, AI.
And that realization is so critical. We've finally moved away from just measuring raw performance.
Yeah.
We're now recognizing that intelligence is fundamentally a strategic choice in how you process and compress the entire universe of information available.
And that right there is the core mission of this deep dive for you, to really
Mhm.
understand this divergence as we head into 2026.
Yeah.
Why are the easy tasks for us humans, the unstructured, high-stakes decisions that need real judgment, still so fundamentally hard for machines?
And the flip side, too, why can an LLM just crush these massive data synthesis tasks
Yeah.
that are completely beyond human capacity? It really boils down to what the goals are. The biological brain, it's been refined by millions of years of evolution to prioritize semantic fidelity, meaning, and contextual richness. It's optimized for survival.
Yeah.
But the current Gen AI models, they prioritize something totally different.
Aggressive statistical compression.
It's all about mathematical efficiency.
Hmm.
That's the optimization target.
And that single strategic choice, that difference, it defines everything we're going to discuss today, right down to the silicon.
Absolutely.
I think the most important thing to grasp right up front is that these LLMs, they live entirely inside a numerical vector space. So for them, certainty is just a high probability.
Exactly. They completely lack direct sensorimotor grounding. And think about what that really means.
There's no lived experience.
None. A machine can read 10,000 pages describing the color red or the concept of heavy, but it has no felt experience of touching a hot stove.
Or trying to lift a 20-pound box.
Right. And humans use that physical feedback to anchor meaning. When AI lacks that, you get what the industry is calling the calibration gap.
That disconnect between the model's statistical confidence and, well, reality.
Precisely. And bridging that gap is the single biggest focus of R&D right now.
Okay, so let's unpack that a little deeper. Let's focus on these two, fundamentally different strategies for how knowledge gets organized.
Let's do it. So the biological strategy is what we'd call semantic contextual. When we learn, we group things, but we do it efficiently.
Right?
We take a robin, a blue jay, a hawk, and we put them all in the mental bucket of birds.
That's compression.
It is compression, but we're really careful to preserve what's called semantic fidelity. We keep the fine-grained details, like the different bird songs, and we also retain the concept of typicality.
Typicality. So we know a robin is a much more typical backyard bird than an ostrich is.
Exactly. And that's crucial because it lets us generalize reliably. But the AI strategy is totally different.
Purely statistical.
Purely statistical. It's rooted in information theory, something called rate distortion theory. It's just math optimized for compression.
Which is great for speed and scale.
Fantastic for it. But that optimization, it often comes at the expense of nuance, of that internal structure, especially typicality. An LLM can generate something statistically perfect, but if you ask for a typical bird, it might blend attributes that never actually coexist in the real world.
It's finding a mathematical average, not a contextually rich, evolutionarily useful example.
That's a great way to put it.
And the physical cost of these two strategies, it's staggering to compare them.
It really is. This is where you see the starkest difference. The human brain runs on about 20 watts of power.
Which is basically a dim light bulb.
A dim light bulb. Now, compare that to a 2025 state-of-the-art AI supercomputer running a big model.
And that can consume
What
up to 50 megawatts.
50 million watts. Wait, 20 versus 50 million? That's not just an engineering challenge.
No. That fundamentally reframes the economic feasibility of deploying this stuff globally. That biological efficiency has to be the guiding star for future hardware.
And that efficiency even extends into how meaning itself is built. Human language evolves to compress these really complex experiences into single words.
But that's a slow social process.
Very slow. LLMs, on the other hand, are rapidly mapping language to this high-dimensional numerical space. And while the vectors tend to line up with our concepts, The models are always prioritizing that statistical efficiency over the deep contextual richness that only comes from, shared human experience.
So statistical compression is running headfirst into a physical and economic wall. 50 million watts isn't sustainable,
Not globally, no.
which leads us right to the hardware shift, the search for agility. We're seeing investment pivot really hard toward what's being called vertical AI.
These are models deeply embedded in specialized, complex industries.
Yeah.
Bioengineering, law.
Right, and that convergence with synthetic biology, especially genomics, is what's really driving the urgency here.
We're facing an existential data challenge. I mean, genomic data is projected to hit 40 exabytes globally by late 2025.
40 exabytes.
We are literally outstripping our ability to store and compute this information. AI isn't just helpful here, it's essential.
And this is where the very structure of biology seems to be fighting back against AI's preferred methods.
How so?
Well, we've learned that standard compression algorithms, the ones designed for linear text based on, say, simple Markov dependencies,
Okay.
they perform disappointingly when you apply them to biological sequences like DNA or proteins.
That's right. To even start making sense of something like protein folding, you need these much more complex architectures, like long short-term memory networks, LSTMs.
To capture the long-range dependency.
Exactly. And this finding that some proteins might be fundamentally incompressible, that's a stunning insight. It suggests the architecture of biological intelligence is a far deeper manifestation of physical laws than we currently get.
And that structural problem points directly back to our computing first principles, right? That 50 megawatt barrier we keep hitting.
You're talking about the von Neumann bottleneck.
The von Neumann bottleneck.
It's the conceptual wall. Imagine a chef, that's the processor, who has to run across a giant kitchen to the pantry. That's the memory for every single ingredient.
For every step of the recipe.
Every single step.
Yeah.
That constant data transport just sucks up enormous amounts of power and time. Our software, written in languages like C++, my is inherently non-agile compared to the brain's parallel processing.
So how do we stop the chef from having to run across the kitchen all the time?
The main contender right now is neuromorphic computing. It's an approach that's designed specifically to bypass that bottleneck by mimicking the brain.
So it's event-driven parallel.
Exactly. Memory and computation are integrated locally at these artificial synapses. Think of chips like Intel's Low-E2 or IBM's North Pole.
And the efficiency gains there are just phenomenal because they aren't computing all the time.
Correct. The key mechanism is sparse processing. The system only computes when a relevant spike, event, a piece of data is detected, just like a neuron firing.
So you go from megawatts.
Down to milliwatts.
Yeah.
We saw the SPEC chip this year from the Chinese Academy of Sciences. It consumes only 0.42 milliwatts when it's idle. That kind of efficiency completely changes the game for edge computing.
That sounds revolutionary. I mean, the numbers are just mind-blowing. But let me ask the skeptical question.
Go for it.
If these neuromorphic chips are so efficient, why haven't they replaced GPUs everywhere? What's the catch?
That's a great question. The catch is that they are specialized. They are fantastic at pattern recognition, these sparse, event-driven tasks.
Like a security camera that only turns on when it sees movement.
Perfect example. But they're not general-purpose computing solutions, not yet. And programming them is a completely different paradigm. You have to rethink algorithm design from the ground up.
So the goal is to scale them up and make them more versatile.
Exactly. To handle the complexity of large language models, not just simple sensory tasks.
Okay, so we have this hyper-efficient, specialized hardware on the horizon and statistical models that are great with data, but all that efficiency doesn't mean AI is ready for the real world.
Not even close. We're running into what developers and agronomists are calling the reality gap.
The reality gap.
Absolutely. Take reinforcement learning, RL. It's amazing in simulated environments, right? These perfect digital spaces like a harvest game where the ground is always flat.
And the weather is predictable.
Right. But you move that same RL agent to a real commercial farm, and it just collapses.
Because the real world is messy.
Infinitely messy. It's an unstructured field environment. You have sudden pest outbreak, weird weather, uneven soil, a patch of mud the model never saw in training.
And the current models, they're trained on averages.
They are. They rely way too heavily on best-case scenarios and fertile soil. They lack that sensorimotor grounding to handle true, unexpected novelty.
I remember reading about agronomists really pushing back on this, calling for bottom-up approaches. They need models grounded in the local dirt, not just the global satellite average.
And that reality gap has immediate, measurable economic impacts. Just look at the sheep industry.
Okay.
Genomic selection accuracy, which is vital for breeding, is reduced by 10 to 20%.
Just from bad data?
Just from pedigree errors,
Yeah.
inconsistencies in the raw, messy data collected out in the field. The fidelity of the input matters just as much as the fidelity of the model.
So the physical world is messy. Shifting gears a bit, the software world is starting to look half-automated.
It really is.
Over 90% of developers are using AI assistants. We've got vibe coding, natural language coding, as the word of the year for 2025.
And in major firms, something like 30 to 50% of the new code is AI generated.
It sounds like we've hit a capability peak there.
It sounds like it.
Yeah.
But the rigorous benchmarks, they tell a much more nuanced story when you ramp up the complexity. On simple, isolated tasks, like fixing a tiny bug in one function, the top models score incredibly well. Around 80.9% on the SWE bench verified benchmark.
So simple fixes are basically trivial now, but what happens when the task needs architectural understanding?
And that is where the capability gap is just laid bare. You shift the task to complex multi-file reasoning, what real software evolution is, and performance just plummets.
How badly?
On the advanced SWE EVO benchmark, a model like GPT-5 scores only around 21%.
Wow, from over 80% down to 21, that's not a scaling problem. That feels like a deep reasoning failure.
It is, and senior developers are adamant about this. The AI can generate the syntax flawlessly, but it completely fails when it needs to understand the complex business context.
The why behind the code.
The why, or perform deep system design with trade-offs across dozens of files. It could write a beautiful poem, but it can't design the library that holds all the poems.
Okay, so we've got this intellectual split, a hardware crisis, a performance ceiling. How is Wall Street looking at all this as we close out 2025?
Well, the investor market has clearly moved past the primordial soup phase.
The Wild West is over.
It is. Capital expenditure is stabilizing. And big tech's massive data center build-out is actually acting as a kind of compute subsidy for the smaller startups.
So the barrier isn't just the cost of compute anymore.
It's the efficiency of using it. And the model race itself has solidified. We're not talking about hundreds of competitors now.
Right, it's narrowed way down.
Correct.
Yeah.
The race is narrowed to 5 major players: Microsoft OpenAI, Amazon Anthropic, Google, Meta, and xAI. And each one has developed a kind of strategic superpower to survive.
So for Google, that superpower is full vertical integration.
Totally. They control everything from their custom TPUs up to the data centers and the research labs.
Whereas Meta's edge is its mastery of open source.
Right. Leveraging the Llama models to just dominate distribution and the global research community. They're the standard bearer outside the closed labs.
Speaking of shifting consensus, we have to talk about the DeepSeek moment from early 2025.
Oh, that was a tectonic event.
It completely changed how people thought about scale versus efficiency.
For years, the Silicon Valley consensus was just brute force scaling. Spend billions, get the best chips, build the biggest data centers.
And DeepSeek just upended that.
Completely. Coming out of China, they showed the world how to train highly performing open-weight reasoning models at a low cost. It proved there wasn't a mandatory billion-dollar entry fee for world-class reasoning.
So it proved that efficient statistical compression was more important than just massive scale.
Exactly. And that instantly redirected global research toward training, efficiency, and democratization. Because if you can compress the knowledge better, you need less raw power to get the same result.
And that shift from just scale to reasoning is now reflected in the models themselves.
It is. Researchers are now prioritizing these reasoning models, the ones that can show their chain of thought, like DeepSeek R1. And that open model is now genuinely competitive with the closed American models on core reasoning tasks.
And we're seeing this intellectual shift in the whole ecosystem, right? Less hype, more substance.
We call it the denoising of the AI discourse. The big, long-form discussions on channels like Lex Fridman or Dwarkesh have pivoted from just celebrating scaling laws to talking about the soul of open source and the nature of intelligence.
You're also seeing the rise of these more localized, deep dive communities.
Like Stephen Data Talk in Europe. It signals a move towards slow media, deep, meaningful, rigorous conversations. It's a real contrast to the rapid-fire competition happening inside Silicon Valley.
So let's bring it all together. What does this duality, this tension between biological meaning and artificial efficiency, what does it mean for the 2026 horizon?
I think the overarching theme is execution and alignment.
Okay.
The foundation has been built. Now we have to make it useful, efficient, and grounded in reality. The focus for next year is pretty clear.
First up is agent orchestration.
Right. Moving beyond the single AI agent to networks of agents that can collaborate on long, complex projects.
Like designing a whole piece of software, not just fixing one bug.
Exactly. Second is neuromorphic scaling, taking those milliwatt range chips and scaling them up to bring efficient AI learning directly to mobile and edge devices.
Bypassing the big, energy-hungry data center.
hmm And finally, semantic realignment. This is the core intellectual challenge.
Right. Bridging the LLM's statistical efficiency with our human need for contextual richness and meaning.
Making sure the AI not only sounds right, but that it actually understands the consequences of what it's saying.
So, in summary, AI has mastered the pixelverse of images and the codeverse of syntax.
But the reality verse, the messy, unpredictable, physically grounded world that remains the ultimate benchmark, the journey towards truly grounded contextual understanding, it has only just begun.
And that leaves us with a final thought for you as you track these developments over the next year. Remember the fundamental principle that governs both biology and AI design, and this comes from deep rate distortion research. Intelligence is approximately the ratio of adaptive utility over information complexity. Biological systems solve the soul of intelligence by optimizing that ratio for low power and high meaning. The journey for AI to encode that same strategic choice to find maximum utility for minimum informational cost is far from over. So the question is, what new strategic choices will define intelligence in the coming year?